Section 3. Boyle's Law and the Cartesian Diver. Chem Talk. Boyle's Law. Pressure. As you saw in this investigation, gas is easily compressed. It will fill any container and mixes completely with other gases. The observation and study of gases have led to various natural laws. A natural law is a summary of observed and measurable behavior. An Irish chemist, Robert Boyle, was one of the scientists whose work played a valuable part in the development of the natural law of gases. Robert Boyle was the 14th child of the first Earl of Cork, Ireland. He wrote The Sceptical Chemist in 1661, stating that supposed elements must be tested to see if they were indeed simple. If a substance could be broken down into simpler substances, it was not an element. Boyle is also credited with carrying out the first quantitative experiments on gases. He presented to the scientific community a law that relates the pressure and volume of gases. One familiar property of gases is that they exert pressure on their container. When you blow up a balloon, the air molecules inside the balloon collide with the sides of the balloon, exerting pressure to keep it inflated. Pressure is defined as the force exerted per unit of surface area. Pressure equals force divided by area. As you pushed on the syringe to compress the gas, you could feel the pressure of the gas on your finger. Pressure can be measured by using devices like a barometer, as shown in the diagram. A glass tube is filled with mercury and inverted into a pool of mercury that is open to the air. The mercury in the tube falls, but only a short distance. The air is exerting pressure on the pool of mercury and keeps the mercury in the tube. Under normal conditions, the pressure of the air pushes the mercury to a height of 760 millimeters. The units of measurement for pressure are atmosphere, ATM, or millimeters of mercury. The relationship between the two is 1 atmosphere equals 760 millimeters mercury. In the metric system, which stands for, in SI, which stands for System International Units, a modern international version of the metric system, the unit used for pressure is kilopascals. 1 atmosphere equals 101.325 kilopascals. And SI is also known as the metric system. Relationship between the pressure and the volume of a gas. Boyle studied the relationship between the gas pressure and the volume of a gas trapped in a tube. He described what is now called Boyle's Law. For a given amount of a gas at a constant temperature, the volume of the gas varies inversely with its pressure. That simply means that when the pressure increases, the volume decreases. When the volume increases, the pressure decreases. Imagine a group of 15 students. They are all running in straight lines in the classroom at top speed, hitting and bouncing off the walls. The additional pressure on one classroom wall will be determined by the speeds of the student and how often the students hit that wall. If the same 15 students now moved to the gymnasium and ran in straight lines at top speed, the number hitting one wall in a given time would be less than in the classroom. This is because the walls are larger and also because it takes a longer time for the students to get from one wall to the opposite wall. The kinetic theory of matter provides a way to understand what is happening to gases at the nano or molecular level. The particles of a gas are moving about with a range of speeds and corresponding kinetic energy. These particles can collide with the walls of a container. These collisions create the pressure, or force per area, on the walls of the container. When you increase the volume, or the size of the container, the number of gas particles hitting any section of the wall in a given time decreases, and the pressure then decreases. It's similar to the students going from the classroom, small volume, to the gym, large volume. When you decrease the volume, when you make the container smaller, the gas particles have less distance to go before they hit the walls, and so the particles will strike the container walls more often and create a greater pressure. This behavior can be represented mathematically as pressure times volume equals a constant, or pressure times volume equals constant. Where K is a constant for a given sample of air at a constant temperature, it can also be represented graphically as shown. The pressure times volume of each point on the graph is identical. In this investigation, you started with a fixed amount of air in a syringe. When you push the plunger in, you squeezed the air into a smaller volume. The molecules of air inside the syringe were then colliding with the sides of the syringe more often, and the pressure increased. You felt that pressure on your finger. You measured the additional pressure with the number of books that could be supported by the gas. You can use the following equation to calculate the new volume of gas when the pressure has been changed, or the new pressure of a gas when the volume has undergone a change. The equation compares the initial and final pressures and volumes. P1 and V1 are the initial pressure and volume, and P2 and V2 are the final pressure and volume at constant temperature. Initial pressure and volume, final pressure and volume at constant temperature. Example, suppose you have 1 liter sample of oxygen gas at a pressure of 1 atmosphere. If the pressure were increased to 2 atmospheres, what would be the resulting volume? Rearrange Boyle's law equation to solve for volume 2. Volume 2 equals pressure 1 times volume 1 over pressure 2, which was pressure 1 was 1 atom. The volume for 1 was 1 liter. Volume 2 is a half liter. The final volume would be a half liter. This is the volume you would predict. The pressure was doubled, so the volume was decreased by 1/2. The Cartesian diver toy can also be explained using Boyle's law. When you squeeze the container, the volume of the air decreases, causing an increase in the pressure of the air. This increased pressure drives the diver down into the water. If the diver is an eyedropper, you can see how the extra pressure on the water drives more water into the eyedropper. This increases the density of the eyedropper and it sinks. Pressurized airplane cabins, tennis balls, and scuba diving are some of the applications of this pressure Volume law.